Our speaker today is Spencer McIntyre. He works for Secure State. He's a vulnerability researcher, and I will let him take it away from here.
All right, thanks everyone. Can you all hear me in the back? No? No, you cannot. How about now? Is that better? Okay. Oh. My bad. Yeah, I don't want to listen to that. All right, so my name is Spencer McIntyre, and we're going to talk about the Windows subsystem for Linux. All right, so real quick, here's the agenda of what we're going to go over. We're going to talk real briefly about who I am, but then we're going to go right over into the Windows subsystem for Linux overview. So if you haven't been keeping up on it, we're going to just do a real quick overview of basically what Microsoft has said. But then after that, we're going to go over, I wanted to take two approaches to this talk. I wanted to talk about the real gritty details, the technical details of how this subsystem actually works, what it is, what it might mean if you're looking for bugs, if you're a vulnerability researcher, the kind of things that you'd be looking for in that. On the flip side, I kind of wanted to take another sort of higher level approach and kind of apply these to what this might mean as your job for a penetration tester. So just so I can kind of get a feel for the audience, how many of you here are actually in the business of penetration testing? Okay, so a good number of you. Okay, anybody like bug hunting, vulnerability researchers, like real technical? Okay. So yeah, so there's a couple of you. So hopefully there'll be enough for everybody. But yeah, we're going to talk about the implementation details and how this might affect you. And then in the second half, we're going to talk about what this actually means, the types of things you might want to look for, things like that. So that's going to be in those attacker notes. So real quick about me, like she said, Mr. McIntyre. I work for Secure State. I've been there for a little bit over 5 years now. I was on the penetration testing team. I am now head of the research and development team. So we do vulnerability research, primarily a lot of tool development as well. I do a lot of Windows kernel stuff. I like Windows internals. So I induce a lot of BSODs. There's a lot of that. I'm an avid open source contributor. I really believe in open source. And one of the things I am most proud of is I'm actually one of the members of the Metasploit team. So really proud of that. But I'm also a Python enthusiast, and so that's enough about me. All right, so the overview of what is this Windows subsystem for Linux, or what we're going to be referring to as WSL. So the objective of this project, of what Microsoft wanted to introduce, was the ability to be able to run 64-bit ELF executables that are built and intended for Linux on Windows as a native solution. This is not virtualization. A lot of people might be getting this confused with virtualization, and one of the key points about this is that there is no virtualization level in between. What there is instead is there is actually a couple of drivers, which we're going to go over in some details, that allow executables to be run on the native hardware of Windows. So because it's not virtualization, and this is a key point, these executables are going to be running at native speeds of about as fast as you would expect them to run on a full-blown Linux system, because you're not going through all those other levels of the virtualization and that scheduler that ultimately gets down to the host. There's none of that. It's on the Windows hardware, so it's not virtualization. It's a bit more akin to like a container type of architecture. So one of the big things is like all the Linux processes that are running in the WSL environment are referred to as Pico processes, which is kind of a newer term and it's kind of a newer concept for Windows, but it's actually been around for a little bit. And we're going to talk about Pico processes pretty extensively. Now, the functionality that's actually leveraged by Windows is provided in two particular drivers. There is the LX core driver, which implements the functionality that you're actually using. It implements the drive file system, so the ability to read and write files, as well as interact with the kernel, and I do air quotes around that because there's not actually a kernel, but it emulates the ability to get kernel settings, in some cases change those settings and things of that nature. As well as there's the LXSS. Now the LXSS driver is actually very interesting. Sort of this architecture of these two drivers is most of the functionality is actually provided in the LX core driver. The LXSS driver is very, very small. It's about 1/20th of the size of the LX core driver, but it's actually the primary namespace. And so it's going to be what is actually managing and sort of providing all this functionality to Windows at a higher level, but underneath its hood, LXSS is utilizing LX core. So this is a diagram. First and foremost, I did not make this diagram. This is the only sort of image I kind of stole from Microsoft, but this is how all the processes are actually intercommunicating. So when you're on your Windows system and you utilize bash.exe, you're going to communicate with the LX session manager, and that's going to be over the COM communications. That's then in turn going to issue an IOCTL routine, and that is going to call that LX sys driver, those drivers that I referred to before, which are then in turn going to initialize the subsystem and start to provide the functionality that you would expect. Now, the subsystem is initialized exactly once per user. So if you open up cmd.exe and you run bash in 2 or 3 windows at the same time, it's only going to initialize it for that first one, and the remaining windows are all going to share what is going to be the pseudo Linux container. So those are all going to be together. So the first time that actually runs is going to initialize all the information that's necessary. It's going to start that init process, and ultimately the native 64-bit bash elf executable is going to run. This is going to allow you to run things like apt-get, Python, sed, awk, grep, all your favorite Linux command line utilities. OK, so implementation details. Like I mentioned, the LXSS driver does not actually have a whole lot of functionality within it. It is a very small driver. When the LXSS driver is actually loaded, its entry point simply calls the LX initialize routine that's provided by the LX core driver. So we have this sort of laid out right here. Moving down is sort of time of how these drivers are actually loaded. So the service, as the system boots up, is going to load the LXSS driver, which is going to call an exported function within LX core, and is going to pass it its driver object. Now, when LX core gets that driver object, it's actually going to initialize all the internal structures that Windows expects a normal driver to register. So it's going to register all those functions in the major functions array, the driver entry point, how to unload the driver, and all of those things. Those are actually all done in LX core. But what's kind of sort of interesting about this is that LX core is registering all of these under the name of LXSS. So the LX core driver, when that one is actually initialized, its driver entry point doesn't do anything at all. There is no LX core driver from an object perspective in the Windows kernel, because while it exists there in a sys file and the PE executable is loaded, there is no driver object that is initialized specifically for it. All right, so Pico processes. What are these Pico processes? So these Pico processes are a lot different than the native Windows processes that we're used to using on a daily basis. You know, whenever you run like Internet Explorer, calc.exe, anything like that, these are full-blown Windows processes that are using the Win32 like API and subsystem and all of that. Pico processes are more similar to hollow container processes. It is a process level structure in the kernel, but as far as Windows is concerned, it's running but not a whole lot else, as well as those processes have a limited access to the outside environment outside of it, which we're going to talk about a little bit in the attacker section. So Pico processes are not specific to the WSL system at all. Pico processes have actually, they came out of Microsoft's Drawbridge research, and they've actually been around since Windows 8.1 and Server 2012. That's when the functionality was actually included inside of Windows. Now, to my knowledge, there's actually no other major uses of Pico processes. So while these have been actually around for quite a while, the functionality all existed in Windows. It hasn't been until recently that this functionality is actually exposed in a way that's actually usable from beyond sort of like a research computer science perspective. But now it's actually usable by using the WSL system for an end user. So they're going to leverage this Pico process functionality. Originally, the Pico processes were introduced by Microsoft as a new form of sandboxing. So these hollow processes don't actually contain the structures that a standard Windows process has. So when you run and start a new typical process on Windows, you start calc.exe or notepad.exe or anything like that, you're going to get a copy of NTDLL. You're going to get a shared memory region by the pointer of user32 in memory that facilitates reading objects out of memory and shared with the kernel, and it's there for performance reasons, so you don't have to switch the context all the time. None of this actually exists in a Pico process. It is a hollow process structure, and so the access that it has outside of that is very limited because it does not have any of these APIs. one of the other changes that it has is it actually has a separate syscall interface, so that when it makes a system call and it transitions its context into the kernel, it's not executing the same code that a standard Windows syscall would utilize. But a key point about the Pico processes is the Windows kernel is still going to provide the functionality that's leveraged by threading as well as memory management. The real basic low-level stuff is still going to be handled by the Windows kernel. All right, so like I mentioned, Pico processes get a separate system call dispatcher. Now this is very important because this is how those 64-bit Linux binaries are going to expect to communicate with the underlying system. The system call interface and the file system interfaces are kind of the two largest interfaces that the Linux binaries are going to expect to be present in order to be able to execute on a system, thinking that they're actually on Linux. So when the LX core driver is loaded and it initializes that LXS driver object, it registers itself as a Pico process provider. And as part of this, it is stating to the Windows kernel that Pico processes that are associated with it have its own system call interface. And that is how system calls that would normally expect to go through Linux are actually being routed through the LX core driver, which actually ultimately provides the functionality. So now this is very important. So now all the system calls are actually implemented in LX core. Excuse me, I shouldn't say all of the system calls, but all of the system calls that are implemented in LX core. So one of the first things I wanted to actually look at when I started this research is I wanted to look at what system calls are actually implemented. So now this is going to directly affect what binaries are going to be able to successfully run on Linux versus which ones are not quite going to be supported yet. So the WSL system reports that it is a Linux kernel 3.4.0. So when I pulled down the source code to that and I looked at all the exported system calls and I compared those to those ones that are actually provided in the driver, about 62.6% of system calls actually are implemented. The remaining system calls are going to error out, and binaries which leverage those system calls they're not going to be able to run. They're going to have segmentation faults. They're not going to be able to utilize the functionality that they would expect to be available. Some of the notable missing system calls are actually 32-bit equivalents. Now, the standard ones that the Linux kernel provides that don't have the suffix of 32-bit are typically utilizing a 16-bit structure. So the 32-bit equivalents, which are some of the newer ones, are some of the system calls that are missing in the WSL environment. OK, so when a 64-bit Linux binary runs, it's going to start to make a bunch of system calls. There's going to be memory map regions. It's going to need to open processes, all these kinds of things. And it's going to expect that the kernel that it's running on, in this case the Windows kernel, is going to be able to handle those. So when a call is actually made, it goes into the system call dispatcher that's provided by Windows, which notices that the process is a Pico process, and it's registered to the LX core driver, so it ultimately gets routed to that. From there, the LX core driver is going to either it's going to modify the arguments and forward it to an equivalent Windows system call if one is available, such as NT create file, NT. All those system calls that Windows provides to be able to do file operations, memory management, things like that. Those, of course, all exist. So the LX core driver is going to modify the arguments so that they can be forwarded and provided and fulfilled by the Windows kernel. Now, in certain conditions, the Windows kernel does not actually have an equivalent system call. And in those cases, LX core is going to fulfill it itself. So the point of this is that it's either going to translate the system call or it's going to fulfill it itself for all those 62.6% that are actually implemented. Now, when the calls are actually made, because these are being made by Linux binaries, these are not using the standard Windows calling convention. It's both of them utilize the RAX register to implement to pass in the system call number, but all the parameters are different in Windows versus Linux. So it's going to utilize this alternative calling convention, and Windows just simply forwards that on to the provider, and the provider handles that itself. So this might be a little bit difficult to see, but this is actually the call stack for when a system call is made to mmap. So depending on if you are going to be bug hunting or if you're going to be reverse engineering, this bottom entry down here is going to be the initial dispatcher. When the context is switch over from user mode into kernel mode, that's going to be the first one that gets it, and it's going to realize that it's a Pico process, and it's going to dispatch it to the PS Pico system processor dispatcher, and then from there it goes into LX core, which is this LXP syscall dispatch. So it's going to pass it over to the LX core driver to dispatch it however it sees fit, and then LX core ultimately maps it into an LXP sys_mmap, which is going to fulfill the mmap system call. So why this is useful is that if you're trying to reverse engineer the implementation of a specific system call because you want to look at it for vulnerabilities or anything along those lines, it's very important to know where exactly you can set your breakpoints so that you can actually start to look. So if you wanted to catch all system calls that are from Pico processes, you could do that third one, that middle one, as well as if you only wanted Pico processes for LX core, that second from the top. Ultimately, if you just wanted mmap, you can do that top one. So you can actually go in and register that. Something else to keep in mind is that if you actually did want to look at mmap, there are a ton of mmap calls. It's going to be very difficult because every process is constantly like allocating memory. If you just do like ./ and run basically any binary, you're going to get hammered with all of these calls. So in order to filter them, you need to remember that this is going to use the calling convention that is utilized by Linux and not by Windows. So it's going to use that RDI, RSI calling convention that's actually also specified by the system v ABI. All right, so next up is the file system. So this is the other major way in which Linux communicates. Whereas on Windows, almost everything is represented as an object. You have objects for processors, or excuse me, processes, objects for threads, objects for drivers. Everything is an object. On Linux, Linux does things a bit differently, and a lot of interactions are actually done through the file system. On Windows, if you want to get information about a process, you open a handle to the process object. Then you can use the Win32 API to query information, change information, things like that. On Linux, Linux actually exposes this information through a special file system, and then you can read the files on that system to be able to process out the information. So it's exposed actually through the file system. But there are actually two major file systems that are provided by Linux. So there is the VOIFS, which is the virtual file system. So now this is going to have the Linux root directories. This is going to have etc, lib, var, opt, all those directories that typical files exist in. One of the important things to note about this file system as opposed to the other is that it is not accessible through Windows. One of the interesting implications of this is that if you were to store a malicious file that would typically trigger like an antivirus exception on this file system, you could store it without worrying about it getting picked off because it is not actually accessible through the Windows environment. There are no APIs currently documented and exposed by Microsoft for reading this file system.
How about the other way?
Yes, the other one is the DriveFS. Oh, the other way. Yes, using the DriveFS, you can access all the file systems on the Windows root drive, barring permissions, which we're going to talk about. So his question was, what about the other way? So the other file system is the DriveFS, which allows access to all of the Windows drives. So when you are in your bash.exe, if you want to access a file in your C users Spencer desktop directory, you can do that, and Windows kindly mounts the C drive under /mnt/C. So all of your drives are going to be mounted there under C. And then you can access all of those files, and there's some nuances that we're going to talk about. So those are the major file systems for reading and writing your standard typical files. Now, the other file systems are actually implemented for proc and sys, which allow basic communication with the kernel. That's what they're used on a full native kernel implementation. You can read out information about the networking configuration. You can read out processes. You can get kernel options at runtime, things like that. These are implemented in very limited fashion on the WSL, so you don't have access to nearly even close to all of that you would expect to have on a normal Linux system. Specifically, one of the things I wanted to call out is the procnet. is not implemented enough for ifconfig to be able to run at this time. It's something I should have mentioned at the beginning of my talk is that the WSL is actually in the Windows Tech Insider program. So you have to opt into it to be able to get this functionality. It is publicly available, but you have to register, you provide your email address, you don't have to pay anything, and then it takes a long time to download. It took me probably about like 6 hours to like download all of the updates. I'm running it in a VM, but it takes a long time to download it. So they are still updating it. So I would be willing to bet a large amount of money that that Microsoft is going to continue to implement the missing syscalls. That 62.6% number is going to hopefully go up, as well as some of the basic file system controls, like the procnet. It's probably going to be one of the ones that's going to be a high priority for them to implement, because right now it's breaking ifconfig. You cannot list interfaces on your system. You can still utilize sockets, you can bind, you can connect, things like that all work, but if you try to run ifconfig, you're going to have a bad time. All right, so DriveFS specific notes. So this is very interesting. This is the file system that allows the WSL environment to be able to access all of the files under the Windows environment. So when a process is created, when one of these Pico processes is created, it's always going to have the permissions of the Windows process that created it. So if I run bash, it's always going to run as me, Spencer. Even when I elevate to root, when I do like sudo-i or something like that, it's still going to run as me, which is something I haven't actually read anything about Microsoft addressing specifically, and this is kind of going to be a common motif throughout the rest of my presentation, is that root really doesn't mean anything. So when you're root and you create a file in the DriveFS, it's going to have all the file permissions. It's going to have 777, and you're not going to be able to change those. You're not going to be able to change the user. And if you try to write a file with like 600 permissions because you don't want your user to be able to read it, and you're doing that as root, all the user has to do is exit out of bash, and they can go over, and from their Windows user, they can access that file, and they have full permissions to it. In addition, if they drop out of root permissions, because you actually can't change the 777, you can still access the file. So what's kind of interesting is that within the DriveFS, the permissions are not honored the way you would expect them to be. All right, so here's kind of an example of this. So I understand this is a little bit hard to read, but up here I'm in the MNT-C directory. So I'm in my Windows users home directory, and I just echo out super secret into a file. And below that, we can tell that the permissions are 777, and the file is owned by root. What I think is kind of problematic, and one of the things that I am predicting is going to be a problem in the future, is this next command where we do chmod 600 on that file. And we actually check the exit code of chmod, and it comes back in the exit of 0. So chmod says, like, hey, there was no problem. We would expect that the permissions on that file would have been updated accordingly, and that file would now be protected. You know, it's owned by root. Nobody else should be able to read it. But right after that, we're able to see that it is still 777, and when we exit out, my user, not root, can still access that file with those permissions. So in my opinion, this is kind of problematic because users that are used to running in a Linux environment, they're going to expect that things would work in the way that they would intend. Now, this is only the case on the drive file system. On the virtual file system, in those Linux files, if you go into like etc, the permissions do work the way you would expect them to work. So if you're root and you go into etc and you know, hopefully your shadow file permissions are 600 and somebody compromises your root user, they're not going to be able to get your shadow file. They're not going to be able to read that, which when you start up WSL for the first time, it prompts you to make a password, so it's not even associated with your Windows password anyways. Also kind of interesting. Okay, so those are all the technical details of how it's implemented. So we're going to talk about what are the implications of this for an attacker, and hopefully you're kind of already starting to see this with the problems of how root permissions are being handled. So one of the first things, I wanted this section to be, you know, if you were a pen tester and you compromised a system that was WSL, what are some of the basic things you would need? So that way we can sort of answer these questions of the low-hanging fruit. So identifying WSL. So one of the first things you want to do, if you're on a system and you suspect that it's Windows on Linux, how would you identify this? This is actually ridiculously easy. There are quite a few different ways. So I have them, and one of the obvious ways is that Microsoft, the actual word Microsoft, is in a couple of locations in relation to the kernel. Despite the kernel being from Canonical and being from Ubuntu, it does say Microsoft in them. So you can search for Microsoft in those titles. You can also look at the MNT directory. You can look to see what exactly is mounted. You should see the drives being mounted in there. So these are things that may in the future be changeable. So Microsoft might update, drop the Microsoft string or whatever if it starts to get abused by attackers. So there's a couple of behavioral clues that I wanted to point out because these ones are probably less likely to be changed because it's not going to be as easy as just dropping the word Microsoft out of the titles. So there's exactly one module in the sysmodules interface. I find this very unlikely on a standard Linux system because you're going to have drivers that are going to be loaded. It's not a sure thing, but chances are pretty good you're going to have a couple of drivers loaded on your Linux system. Proc is missing module entries because there's not a whole lot of files that processes that are running. Additionally, there is no init system. There is no upstart systemd or anything like that. It is very bare bones. So there's no as of this time, there is no ability to be able to register a service in the WSL environment. And probably my favorite, which is actually very interesting, is the strictness of how the flags are passed into the mmap system call. This one I find very interesting because this is definitely a good behavioral clue. And now the standard Linux systems are less restrictive and don't check for the adherence of the flags to the standards quite as much. So what we can actually see right here is in my example call, and I left off the back so that you could have a font that was big enough to read it. But this third parameter right over there, where the permissions for the region of memory that you're trying to map are specified. If you specify 1000 in hex, which is not a standard flag, Linux will ignore it. It just won't change anything. The region of memory will be mapped, and you can go along your way. However, in Windows, if you specify a flag that's not defined, it's going to throw an error code. So if you try to run the same exact function on Linux versus on WSL, WSL will cause it to fail, whereas Linux will have it run successfully. And this is that I was mentioning, 3.4.0-Microsoft. Very, very subtle, but pretty easy way to be able to identify that this is probably not the Linux system that you're looking for. So one of the other things, like I said, I once hit on what penetration testers would really want to know when working in this environment. So the Metasploit framework, what payloads are going to actually work in this environment? So now I went through the list and I tested these. Now each one of these I tested as a 64-bit ELF executable, so using MSF Venom to put the shellcode into your standard ELF file and ran them from there. Something interesting is the WSL system strictly supports 64-bit binaries, whereas on I'm using Fedora. I don't know if anybody noticed, but I run Linux on my hardware. I can run a 32-bit binary, a 32-bit ELF file on my Fedora host, and it works just fine. On WSL, though, it only supports 64-bit ELF executables. So that's why these ones going down. So the Metal payload, brand new. It came out, I think it was 3-4 weeks ago. One of the great works by Brent Cook, and there's a Metasploit blog about it. That one will not work. The reason why that will not work was actually that exact mmap call that I had just pointed out, and that's what we noticed as we were doing the testing of this, is that because the Metal stager needs to be very small. It's a standard exploit stager. Size is very key. It leveraged that nuance in the Linux system that wasn't as strict about checking those flags in order to work, but Windows is being much more strict about those flags. And so in this particular case, the Metal payload was failing with that reverse TCP stager, and it was not actually running because of that. Next up, the unstaged 64-bit shell worked just fine. The So it was your typical reverse shell. You can use it, not Meterpreter, so not quite as good as you would hope. The 32-bit version of Linux, there is no 64-bit version of Linux Meterpreter. And like I said, when the WSL system only supports 64-bit ELF executables, so the 32-bit one is, of course, not going to work. And then last but not least, and not just because I helped out with it, was the Python Meterpreter. This one was the only working Meterpreter instance that worked on WSL. Now, I say that it worked, but there were still some problems in the functionality that it was expecting to leverage, and one of those things was like the ifconfig. So right here we can actually see the output of what I was able to get from the Python Meterpreter running on this, which is the only Meterpreter that ran on it. And so we can see the Linux 3.4.0. Now, this information does not include Microsoft's. Because the kernel version is actually stored in multiple locations, the particular location where sysinfo actually pulls it from doesn't say Microsoft, so it might not be as obvious. But down here, ifconfig failing. This is because even the native ifconfig object on Linux doesn't work. The actual native binary does not function, so Meterpreter's not going to be able to work it out either. All right, so the Linux kernel protection. So because the Linux kernel doesn't actually exist in this environment, it's not there. Microsoft claims to have done a clean room implementation of all the system calls and all the functionality that's provided. There is no Linux kernel. So what I wanted to do is I wanted to look at some of the protections that a binary that's running on a Linux environment would expect to be provided by the kernel. And unfortunately, all the basic ones that I checked for are all actually provided. Now, the reason why all of these are provided between user mode, ASLR, DEP, and null page prevention is all of these are memory protections. And those memory APIs are, of course, going to be very common. And when a mmap call is actually made, it is fulfilled by the Windows kernel. It's not actually implemented by LX Core. So in being fulfilled by Windows, you get all of those protections that Windows already offers. So data execution prevention, ASLR, null page mapping, all those things work as would be expected. Something I did notice, however, and that I did want to point out is that the randomized VA space, that option that allows you to modify how ASLR is implemented on a Linux system at runtime, you actually can control that. So if you echo out 0 in WSL into that control file, you can disable ASLR, ASLR for your session. On the flip side, the null page mapping that's typically controlled through the mmap min address, that is not available, and that's one of those control files that you can't read that, you can't modify it, or anything like that. It's just not implemented. Okay, so cross-process access. So let's say we're going to go over the scenarios of if you have a compromised system in a WSL process, what type of access can you get out into Windows and vice versa? Okay, so this would be desirable, of course, if you're on a pen test. If you compromise, an SSH server which doesn't work yet, Tomcat, or if you compromise the Windows host via some sort of like a SMB vulnerability, things like that. So the bottom line is Linux can't really list Windows processes, and that's because, like I said, Windows processes are stored as objects in the kernel, and they're accessed by APIs, which are Windows system calls, which aren't available because none of that is exposed to the Linux processes. Windows, however, can enumerate out Linux. It can tell that it exists, and it can tell that the processes are there, but the PIDs don't match. So Linux into Windows access, there's not really any functionality for that reason that I'd mentioned, is that you can't actually call the necessary APIs to get the information out of it. You can access other Linux processes through the proc interface. That functionality is available, which is important to know if you need to debug a Linux process using like GDB or something like that. It will work correctly. But because you don't have access to the Win32 native system calls and the API, you can't get into Windows processes. If you wanted to infect the Windows host, what I would recommend doing is going up through the file system and trying to infect some kind of a file from that perspective. Unfortunately, like I mentioned, even if you elevate to root, you're still effectively running as your Windows user. You certainly cannot just go into the C drive and start overwriting DLLs or use like the MOF method and by writing a file into the WBEM directory. You can't do that because from Windows perspective, even though you're root, it doesn't care. You're still actually running as that user, and all those file APIs are all still checking the Windows permissions, which are going to be as the user that you started Bash as. Windows access into Linux, though, is a little bit different. So while you can't access the root file system, you can get a little bit of information available from the processes. You cannot debug any of the Linux processes. Open process fails. And that's because debuggers all need to be able to have extensive access to the process. They need to be able to open it with like process with all the permissions, to be able to read virtual memory, write virtual memory, create threads. They need to be able to do all of that. If you're familiar with the Open Process API, all of the permissions are broken out, and I checked every single one of them, and the only two that you're able to open a Pico process with is the query limited information and the synchronize function. And so another thing to point is like you're not going to be able to migrate into these processes from Interpreter. Interpreter needs to be able to leverage these API calls in order to be able to inject itself over and into it. With the query limited information and the synchronize permissions, though, you can do a little bit of work. You can check to see that, of course, the process is running. Probably the most useful thing that you can do, however, is you can wait for the process to exit, and you can immediately get the status code out of the process. Now, in Linux, when a process exits, the status code is significant. 0 is success, and there's a few other, there's a bunch of other status codes that mean different things from a resource is not available, permission denied, user configuration error, things like that. You can actually get this exit code out of the Linux process from the Windows host by waiting for the process to exit and then querying it with that process query limited information. You can actually get the low 8 bits and get the status that process had exited out with. And so because, once again, the root process is still running as the same Windows user, you can still do the same exact stuff for a process that is running in the context of root. So if I'm on Bash and I start a new instance of Bash as root, if my account has been compromised, somebody can, with my permissions, check and wait for that root process to exit and get the status code so they can tell if it had a segmentation fault, if it wasn't run correctly and there's a configuration problem, anything along those lines. That information is still exposed through the other Windows processes. OK, so the cross-user access. Environments of WSL. So we're talking cross-Windows user access. So in the case of like Server 2012, when multiple users can be logged in and things along those lines. If you install WSL as one user and log in as another, the environment is not there. It doesn't exist. You have to install it again. So it's going to download all those files and it's going to start it up. So because of that, you can't, if both users are running Bash at the same time, they cannot communicate to each other. The file systems are isolated. It's effectively a separate user process for all intents and purposes. There isn't really cross-contamination there. Now, in theory, if you were to elevate yourself up into system or something like that, you could, of course, migrate over into that other user and you'd be able to do it from there. But from two separate user levels, the WSL environment is not shared. OK, so closing thoughts. One of the last things, root really doesn't mean anything. And I'm definitely guessing that that's going to cause problems by users that are expecting to be able to leverage the permissions and the security that, setting a file to user as owner, as root, or anything like that is expected to provide. And I'm going to be guessing that that's going to be causing a problem. One of the things that I forgot to mention that I don't have a slide on is actually that I found interesting was that the repositories that are set up, so when you run like apt-get, there is no evidence that Microsoft has either a certificate installed in there, and there are no Microsoft apt repositories in there. So when you run apt-get update or you're trying to install anything, none of that is actually coming from Microsoft. All of that is still coming from Canonical, like you would expect from a typical Ubuntu installation. One of the last things, so I was doing all this. I was looking through all of the Windows internals. I was trying to find vulnerabilities in the WSL, and Microsoft was kind enough to send me this desktop for being in the Insider program, which has this like sweet Ninja Cat on it. So That was pretty cool. All of these references right here, I started this a couple of months ago, and I spent a lot of time looking into specifically like the system call dispatching functionality. Only for like 3 weeks ago for Microsoft to implement an entire blog that laid it all out and was basically actually like telling me. So that was kind of interesting, but at least I had already figured all that out, and there was no way to really know that they would cover all of that. But those are all my references. Just about all of them are actually from the Microsoft blog series that they have been doing on this. So with that, thank you very much for your time. This is a topic I was really excited to present on, and thank you. We have plenty of time if anybody has any questions. Anybody? Nope. OK, thank you, everybody.